Welcome back. We were discussing the gas power cycles. In the last few lectures, we looked into Otto cycle, which is ideal cycle for spark ignition engines, and diesel cycle, which is a ideal cycle for compression ignition engines. In this particular lecture, we will look at Brayton cycles, which are ideal cycle for gas turbines. Okay, so in reality, the gas turbines operate on open cycle as presented in this schematic diagram, where of course this fresh air is compressed to the conditions of combustion chamber, and it is after the combustion the gas at high temperature and pressure pass through turbine, and the exhaust gas is thrown out. Okay, now you can model this particular actual gas turbine operation as a closed cycle. Okay, and what we can do is we can consider the combustion chamber and replace that combustion chamber by a heat exchanger, which just takes a Q in, and as well as the exhaust process can be replaced by a heat exchanger again, which basically rejects the Q out. So we can consider combustion process as a constant pressure heat addition and exhaust process as a constant pressure heat rejection process. Okay, and that this will make the complete cycle. Okay, which includes a compressor, a heat exchanger, turbine, and another heat exchanger for rejecting the heat. Okay, now one can represent this on a PV diagram and TS diagram. So let us try to represent this Brayton cycle, which consists of 4 internally reversible processes. So one is of course the compressor, which works on asentropic condition. So this will be asentropic compression. So that will be this 1 to 2 on a PV diagram. Then you have this heat exchanger, or basically the combustion, which is a constant pressure heat addition. So that is going to be 2 and 3, followed by 3 to 4, which is asentropic expansion, the turbine, and followed by your constant pressure heat rejection, which is basically the exhaust gas which is thrown out, or represented by heat exchanger again. So this becomes a complete cycle on a PV diagram. TS diagram you can clearly represent as 1 and 2 as asentropic, followed by constant pressure, followed by your again asentropic expansion, followed by constant pressure heat rejection. So we can clearly see how we change this PV diagram from Otto cycle to diesel cycle to Brayton cycle. It's a beautiful way of making use of the different conditions. Okay, now earlier the Otto cycle was both this process 2, 3 and 4 1 was at constant volume, whereas the diesel cycle, the 2, 3, one of the particular cycle was at constant pressure, the other one was at constant volume, and in this case the Brayton cycle was completely a constant pressure heat addition. Okay, so considering that we understand this the idealized closed loop for the Brayton cycle, which consists of these 4 internal reversible process where the heat addition and rejections are at constant pressure, we can do the thermodynamic analysis of these 4 processes. We can apply as usual our energy balance. We will consider the changes in the kinetic and potential energy to be negligible. So what you have is here Q in minus Q out, net heat in. Okay, and then you have this W in minus W out, that will be equal to H exit minus H in. This is energy balance which we are going to consider, but you can consider effectively for each of them separately. For example, in this case Q in is at constant pressure, and this is going to be simply the change in enthalpy from 3 to 2. Okay, and say because this work for this particular heat exchanger is 0. Similarly, for heat exchanger corresponding to heat rejection process, the work is of course is going to be 0, and hence you can consider simply Q in as change in the enthalpy, Q out is change in enthalpy, and this can be represented for the working fluid simply as Cp delta T. Okay, considering Cp is constant for this change in temperature. So this is a simple energy balance. We can also evaluate the thermal efficiency of this ideal Brayton cycle, and we will consider the cold air standard assumption, which essentially here means that the air in this case is going to be considered ideal gas, and the cold means we are going to consider Cp at a typical value of 25 degrees Celsius. Okay, so by definition, of course, efficiency is given by your W net divided by Q in. You can rewrite this as W net is nothing but your Q in minus Q out. Okay, and Q out in this case is going to be Q out in this case is nothing but your H4 minus H1. Q in is H3 minus H2. Okay, and you can replace this in terms of your Cp values, Cp delta T, and Cp will get cancelled as we have considered this to be constant, and thus you can write your Brayton efficiency in this form. Okay, now for the processes of expansion and compressions which we are going to consider in the ideal Brayton cycle are isentropic, and of course we have this constant pressure heat addition, which essentially means your P2 is P3 and P1 is P4. This particular process of expansion and compressions are isentropic. Okay, so making use of this expression, okay, which means the ratio T2 by T1 is P2 by P1 to the power K minus 1 by K, and of course K is your nothing but Cp by Cv. Okay, and considering that of course the pressures are constant for the case of 2 to 3 and 4 to 1 condition, that means that heat rejection and heat addition processes, okay, you can rewrite in this expression. Now this particular expression, okay, can be replaced in this particular efficiency in order to obtain the expression in terms of ratios of the P's. Okay, so what we have done here is that T1 by T2 is replaced by the ratio, and as well as T3 by T4 is also replaced by the ratio in terms of the pressures. And considering these ratios, P2 by P3 is same as P4 by P1, we easily can express this expression in terms of ratios of the pressures. Okay, and then if you can plot this efficiency as a function of pressure ratio, and you clearly can see that as you increase this pressure ratio, okay, you can clearly see that the efficiency increases, and as well as it also increases with the specific heat ratio, okay, which is K. So you can increase the efficiency by increasing the pressure ratio as well as UK. Now, however, for the typical gas turbine, so the pressure ratios are in this region, okay, and other aspect is that the highest temperature in the cycle, which we have seen here, is at 3. Okay, when you add the heat, okay, through heat exchanger, or in a sense through combustion chamber, this high temperature is actually limited by the material properties, because material should sustain this high temperature, particularly the turbine blade, and thus this aspect of the material limits the pressure ratio which can be used by the cycle. Okay, even though theoretically it can increase further if you increase the pressure ratio, but typically it is limited by the material properties, and hence the typical pressure ratios are in this shaded region. The two major applications for gas turbine: aircraft propulsion and electric power generation. Now, as we know, the fact that irreversibility is present due to fluid friction or heat losses, and thus the actual gas turbine cycle will deviate from the idealized one. Okay, the deviation can be characterized in this form on this TS diagram. So, as we know, we have already discussed this 1 and 2. This is going to be isentropic process, the compression. For the case of reversible process, because of irreversibility, there will be a pressure drop, okay, across the pump, and hence there will be some irreversibility. Due to irreversibility, the actual path of this compression would follow in this along this line until this pressure. Okay, and there would be a certain pressure drop during the heat addition as well. So this is the ideal case. Okay, and this dash is basically nothing but your actual process. Now, if you consider the turbine also undergoes a similar operation. So this is your isentropic process, and this would be the case for the actual one, and there would be a certain pressure drop as well, and thus your line, this particular process will deviate from the actual one. Okay, so you can represent this in a more simpler form. And what we are going to consider is in this following way. We can write this TS, okay, This is essentially with isentropic compression, this is your isentropic expansion, and you can show this dashed line as your actual process. So this constant pressure will be here. This will be nothing but your 2A, and this is nothing but 2S, and this is your 4S, and this is will be 4A. Okay, so we can represent this actual and isentropic process in the on the TS diagram in the following way. One can calculate isentropic efficiency of the compressor and the turbine by this formulation. So the isentropic, as we already discussed it earlier, the isentropic efficiency of compressor is nothing but the work under isentropic condition divided by the actual work. Okay, and on the other hand, for the case of your turbine, this will be the ratio of the actual work and isentropic work. Okay, and these works are clearly related to the changes in the enthalpy as we have discussed earlier. Okay, so we can demonstrate this understanding of the Brayton cycle by doing an example, and this is an example of air which is used as a working fluid, okay, in a simple ideal Brayton cycle that has a pressure ratio of 12. A compressor inlet temperature of 300 Kelvin and a turbine inlet temperature of 1000 Kelvin. So I can first draw a TS diagram, okay, and so let me draw this. Okay, so this is nothing but your, this is your 4S, 2S, 2, and this is your 3, and this is your 1. Okay, so what we know is that the turbine inlet temperature is 1000 Kelvin. Now the turbine process is basically 3 to 4. Okay, so inlet will be at 3. So this is your turbine at 1000 Kelvin, and the compressor inlet temperature is 300. So 300 is 1 because this is the inlet of a compressor. Okay. Now what we have is we have to determine the required mass flow rate of air for net power output of 70 megawatt, assuming both the compressor and turbine having an isentropic process. In the first case, when we are considering an ideal condition, that is 100%, and then when you have the actual condition, which is where the efficiency is 85%. Okay, we'll be considering constant heat capacity. Heat capacity from the table, if A2 is given here. Okay, so we can start with simple analysis, and the first thing which we are going to do is make use of isentropic process property. That means your T2S, so, and T1 is going to be your P2 by P1, K minus 1 by K. So from here we can evaluate the other properties, because we know T1, okay, we don't know T2 as, but we are aware of the pressure ratio. So because this pressure is constant, so P1 and P2 is 12, so we are aware of the pressure ratio, hence we can calculate T2S. Similarly, we can calculate T4S because we know T3. Okay, now so we use this information to evaluate these temperatures. Now what we need to find out is the W compressor for the isentropic condition. So let me say in here, this is going to be of course only the change in enthalpy, okay, which is H2S minus H1, and this is can be written in terms of Cp delta T. We are considering the cold air condition, so hence we are going to take the Cp value at room temperature. Similarly, we can find out the turbine work, and that is going to be simply your H3 minus H4S based on your simple energy balance here, and this is going to be T3 minus T4S. Okay, so we can calculate the work in this way. So the net work is the turbine out, okay, minus for the compressor in, so isentropic compressor in, and Now this is, of course, what we have done is we have considered all in per unit mass as a basis, and we have been given the net power output, that is W dot net out is given as 70 megawatt. This is going to be your mass flow rate multiplied by WS net out. Okay, and from there we can calculate your M as W net out divided by WS net out. Okay, so this is how we are going to calculate the mass flow rate. In the second part, we have to consider the isentropic efficiency of compressor and turbine, that is 85%. So we can calculate the W actual net out, okay, is going to be WST out multiplied by your eta of turbine minus WS of compressor in divided by eta of isentropic of C, because you remember that we have discussed this eta of T is WA by WS and eta of C is WS by WN, hence this expression will come. Okay, and after you calculate this, because your etas are given, you can use this expression here to calculate your MA, which is going to be M net out, okay, divided by your W actual net out. Okay, and this is how you make use of this specific simple analysis for the Brayton cycle. Okay, for this is a simple ideal Brayton cycle, and of course we have calculated we have made use of the isentropic efficiency in order to analyze the problem. Okay, now we are going to consider Brayton cycle with regeneration. This is mainly to increase the efficiency of gas turbine engines, and just we'll take a look at the specific conditions. Now, many systems, the temperature of the exhaust gas often is considerably higher than the temperature of the air leaving the compressor. Okay, so this is the case where we can make use of regeneration when you have the temperature of the exhaust gas higher than the air leaving the compressor, which is going to be 2. Okay, and in that case what we can do is we can heat this gas which comes out from the compressor using the heat of the exhaust gases, okay, by making use of counterflow heat exchanger. And this particular way of heating the gas from the compressor by the exhaust gas in a counterflow heat is called regenerator. Okay, so this is the schematic diagram of it. You can see here, this is the inlet of compressor and this is the outlet, okay, which goes to the combustion, and after the combustion high temperature and pressure get expanded, and 4 is the outlet of the turbine. This turbine is essentially used to transfer the heat to the air leaving the compressor, okay, and this is the representation in a steady flow condition. So by making use of this, we try to increase thermal efficiency because less amount of fuel is now needed in order to heat the air from the compressor, and this is something which we can understand from here. So what is being said here, if you look at this 1, 2, 5, these are the representative of the stream conditions. So 1 to 2 is of course the compressor. So 1 to 2 is basically the isentropic compression, and from 2 to 5 there is a heat transfer from the regenerator, which is essentially from 4 to 6. Okay, in other words, you can see that this 2 to 5 is the point where the energy is being transferred from this particular, and where typically we reject the heat. Okay, instead of rejecting this part of the heat from 4 to 6, you transfer this energy to heat up this particular part of the air or this particular process. And this is the reason that this part 4 to 6 is the one which essentially is nothing but your Q regeneration, and this is the part which is taken internally, not from external. Thus you are saving this much energy, okay, and the effective Q in is nothing but from 5 to 6. So 5 is an actual point where you can take it, but theoretically you can raise the temperature till 5 dash which is equivalent to 4, okay, where this 4 is nothing but your exit of turbine, okay. So the maximum heat generation would be your, so regeneration maximum is going to be H5 dash minus H2, which is nothing but H4 minus H2, okay. So this would be the case for ideal case where there is no losses and so forth, okay, and thus your T5 is going to be T4, okay. And but in for the actual case, your Q regeneration is nothing but your H5 minus H2, and the ratio of this Q regeneration to the Q regeneration maximum is we call effectiveness, okay. So this is sometimes called effectiveness, okay. So note that this particular regeneration is useful only when exhaust temperature, okay, is higher than the compressor exit temperature, okay. So as we can clearly see, there is many ways to enhance the efficiency of a gas turbine, and essentially you can think of many other ways. We've already noticed earlier that we've already looked into compressor work can be minimized by intercooling, and similarly we can also increase the efficiency of your turbine by reheating, okay. So this is something which we can try to come up with a Brayton cycle with intercooling and reheating. So this is an example, okay, where I can come up with this kind of diagram T of S, okay. So let's say we have compressor, okay, at 1 to 2, and in order to reduce the compressor work, so we try to cool this, okay, and then we further apply another, we pass through this working fluid through another compressor, so that is going to be 1, 2, 3 and 4, okay, and then we undergo again the same Q heating process at constant pressure. Here we try to reheat, okay, and then we have this connector here, and then of course we can make use of the fact that these temperatures are higher than the exit temperature of the compressor, and thus we can use also regeneration. So this is an example of intercooling. So this is intercooling, okay, and this is an example of reheat, okay, and then of course we can, and this is particular amount, okay, will be Q save. So this is nothing but Q regeneration, okay, and this is going to be reheat. This is your primary heat, this is your energy saved. So thus you can clearly see that this would lead to a better or more efficient gas turbine. Now, as we have discussed earlier, that in order to have minimum work for compressor, so in other words, if you have a two-stage compressor, and to minimize the work, the pressure ratio should be maintained at each stage. That means P4 by P3 should be equal to P2 by P1, okay. Similarly, one can show that for the case of reheat, in order to maximize the work, your P6, which is, so if you can say this is 5, this is 6, 7, 8, 9 and 10, P6 by P7 should be same as P8 by P9, okay. So this is to minimize compressor work, okay, and this is to maximize turbine work, okay. So this is what I wanted to cover, the gas turbine with intercooling, reheat and regeneration, and this will be the end of the lecture. So let me just summarize what we have covered in this particular topic on gas power cycles. We have looked into the Carnot cycle in its value engineering, which acts like an ideal cycle. We have considered the A standard assumption in our analysis, an overview of a reciprocating engine. We have considered three different cycles: Otto cycle for spark ignition engine, and diesel cycle for compression ignition engine. And today we looked into Brayton cycle, which is an ideal cycle for gas turbine engines. We also consider regeneration, intercooling, reheating and regeneration as a part of increasing the efficiency of Brayton cycle. So that will be the end of today's lecture. I will start a new topic in the next lecture. I will see you in the next lecture.